So it's our great pleasure to have here Xuezhou Zhang, who is currently an associate research scholar in the Department of Electrical and Computer Engineering at Princeton University, working with Mangdi Wang. He received his PhD in computer sciences from the University of Wisconsin-Madison in 2021, and he was advised by Jerry Zhu. Prior to that, he obtained his bachelor's in applied mathematics from UCLA in 2016. He is a visitor at Simons Institute for the Theory of Computing Science in spring of 2022. And his research primarily focused on reinforcement learning theory and applications. And today he's going to talk about efficient RL in Block MDPs about the free representation learning approach. Xuezhou, the stage is yours.
All right, thank you, Chava, for the warm introduction, and it's my great pleasure to be here. So today I'm going to talk about our recent work on efficient learning in Block MDPs. So empirically, recent years, we have see a lot of exciting progress in using rich nonlinear functional approximations, in particular deep neural networks, to solve large-scale problems. And these successes is typically are for the cases where we have enough examples to train on. However, in many of these problems, the underlying dynamic is actually relatively simple. So there's often this empirical observation where if you know the raw states of the problem, the underlying latent state, you can actually train a good policy much, much faster compared to if you just train end-to-end from the raw inputs. So the question here is, can we push this red curve closer to the blue curve? Can we close this gap? So the approach we take in this line of work is what we call representation learning. So representation learning is a way to modularize the RL problem from a raw high-dimensional input to a policy. So what we do is we want to first train a encoder, right, that encode the high-dimensional input into a low-dimensional representation. And then on the low-dimensional representation, you can apply any standard RL algorithm and hope to get a small sample complexity to achieve a good policy. All right, so that's enough about the introduction. So let me go over some of the technical setup that I will be using in this talk. So in this paper, we're focusing on the episodic finite horizon MDPs. So there are a total of big H number of time steps. For each little h, the policy takes an action and the environment generates a reward and a transition according to these time varying reward and transition function. And then the objective of the learner is to find a policy that maximizes this total cumulative reward. So I also just want to mention that here we're studying the online setting. So the learner tries to find this policy by interacting with the environment. And for simplicity here, we assume a fixed initial state as 0. So this talk will be like the title is about block MDPs, but I'm actually going to introduce low rank MDPs, and a lot of the later discussions are going to be using the terminologies for low rank MDPs. So low rank MDP is an assumption on MDP transition structure where we assume there is a low rank decomposition of this transition matrix by decomposing to a function on SA and another function on S prime. So in particular, we'll assume that there exists some unknown mu star and phi star such that the real transition can be decomposed by the linear product of these two functions. So it is worth emphasizing that we use low rank MDPs to distinguish from linear MDPs. In particular, here we're assuming in the low rank MDP, we're assuming a unknown phi star and mu star, whereas in linear MDP, you assume phi star is null, right? So that is the main difference. Now, the particular problem that this paper analyzed is what's called a block MDP. So, so a block MDP is a kind of representation where the encoding happens mainly on the state space, right? There's no encoding on the action space. And you assume there is some latent state Z, and it belongs to a finite set of latent state. And then there's a function that maps from raw input or from raw observations to latent state. And then transition happens in the latent state space. So given latent state Z and action A, you will transit to some next latent state. And then there is a emission probability that given Z prime gives you the next observation S prime. So I just want to mention that, previously block MDP has also been called rich observation MDP. The model are exactly the same, but the difference lies in whether you use function approximations to estimate this encoder and the emission distribution, or you are just assuming there's a finite observation as well as finite latent state and use a tabular representation. So that was the main difference. All right, so here is an observation that block MDP actually belongs to low rank MDP. Why? Because we can, if we write out the transition precisely, we can actually decompose it into a structure like the low rank decomposition, where phi star will be a one-hot encoding of psi star S comma A, right? So it is a S times A, it's Z times A dimensional one-hot encoding, and mu star is the emission probability times the transition. Is there a question in chat? Do I?
Yeah, you can maybe answer this question quickly. Alexandra was asking whether the supports of emission distributions for
That's
different Zs are non-overlapping.
yes, they are all overlapping. So it's a decodable situation, right? So
Right.
each observation only correspond to a unique latent state.
Yeah, it's implied by the first condition that you have, right? That
Yeah, it's implied by this encoder. Yep.
Okay.
Yeah, thanks for the clarification question. Now, before I jump into our own results, I just want to touch on the broader context. So, there are, in the past 2 years, there are a lot of progress made on sample efficient RL. And if you look at the class of problems that these algorithms solve, many of them go beyond block or low rank MDPs, right? So here you see the low rank MDP over here. And then there are more general model classes like small Bellman rank, Bellman-Luda dimension, witness rank, bilinear classes. All of these, like algorithm designed for all of these classes, can solve block MDPs. So you might ask, well, why bother study block MDP in 2022, right? If it's already solved. The question is computation. All right, so if you look at all these methods and which one of them are computationally efficient, actually we only know tabular MDPs and linear MDPs with small action space are rigorously computationally efficient, meaning you can give a polynomial space and time complexity for these algorithms. Anything beyond that, we don't have a clear characterization of their computational complexity. Now, there are a slightly larger bubble here where there exists what's called a oracle efficient algorithm. So these algorithms are they're designed so that they only incur polynomial number of calls to a particular computational oracle, right? So these oracles are typically widely accepted in machine learning. So these methods are also considered efficient. Now, if we look at all the efficient algorithms or all the Oracle efficient algorithms that are previously proposed for either low rank or block MDPs, there are 5 of them. So we have Flambe and RepUCB. They are model-based algorithms, and they both solve low rank MDPs. So this is the previous work that Masa talked about 3 weeks ago. And then on the model-free side, there are 3 algorithms. But notice that both prior works, Malfoy and Homer, they rely on this reachability constant. So eta mean denotes the maximum probability of reaching any particular state, right? So if one particular latent state is very hard to reach or not reachable at all, this eta mean will be close to 0, meaning the sample complexity will blow up to infinity. All right, so how to design Oracle efficient algorithms without this reachability constraint is an open problem prior to our work. So here BRIE, which is our algorithm, solves this. We do not incur any dependency on the reachability constant. And we're also a reward-driven algorithm. Right? So all the previous algorithms are reward-free, meaning they can't adapt to a beneficial or helpful reward signals, even if they exist. And we'll quickly, we'll see that later in an experiment. So just to tease you a little bit, that our algorithm actually works. So here I want to quickly show an example of experiments. So here we have a classic combination lock challenge. There are 3 chains of states. So right now everything's still in tabular. We have finite states and finite actions. And in this particular example, there are 10 actions. Among all the 10 actions, only one action is the good action, which can let the agent stay in the good state, right? So we call the white circles good states. And if you perform a bad action in any state, you will transit into the gray state and be stuck there forever, right? And in terms of reward, there's no reward whatsoever in the first h-1 stage, and you will see a good reward. Reward 1 if you successfully reach to the end of the good chain. Otherwise, you will have the reward 0. So it's not hard to see on this environment. If you have like a random exploration policy, it'll take an exponential time for you to hit the goal, because every time step you will have a small probability of making a mistake, and that add up exponentially. So this is a tabular MDP, and in order to encode it into a block MDP, we can embed these latent state into one hot encoding and then do a linear transformation to map them into a higher dimensional space. So this R100 state space is what actually the algorithms are able to see rather than the latent structure. So on this, relatively simple example, can previous methods solve it? It turns out that they can't. Right, so the first thing we try is we want to see if linear MDP in the kernel space solve it. It turned out that it doesn't solve it beyond a depth of 12. And then a deep RL baseline, proximal policy optimization, even when equipped with a heuristic exploration bonus, R&D, still fails at depth 25. The only algorithms that are able to solve it are our algorithms, BRIE and Homer, which is the previous state-of-the-art algorithms for block MDP. But you can see here, our sample complexity is slightly better than Homer, but we'll see more comparison later. All right, so
Can I
just
ask
looking
a
at the
quick
question.
question?
Yeah.
Like on this figure, if you would need to guess based on this figure, like how does the sample complexity grow with the horizon? Is it quadratic or it's not linear for sure?
It's definitely not linear. Yeah,
Right. Okay.
it's yeah, it's probably quadratic.
Something faster.
It's interesting that like all of these they follow kind of the same trend, even though they fail at
Right.
25 or 12, but they're
Yeah.
sort of the same trend. Yeah.
And when you say that they fail, you mean that after that, what
Oh,
happens?
oh yeah. So we have a fixed budget for them to explore. Say like 5 million steps, right? And if they can't learn or they can't reach the goal at all in 5 million steps, we call that a fail. Because you could run them forever potentially, and they will eventually get there. But
So what's on the y-axis? This number of episodes?
though, yeah, it's number of episodes. So you notice that both
Okay.
Homer and Brie are about 3 million episodes before they reach depth 100.
I see. It's like a pure exploration kind of thing almost. That you just want them to get to the end and you measure the time. So they
Yes.
need to systematically go through things and like, okay,
Yeah.
I see.
Yeah, because you see no reward whatsoever in the
Right.
before you reach the goal, so it's as if you're doing reward-free exploration in this particular example.
Yeah. Yeah. Okay. Makes sense.
All right, cool. Yeah, so if there
Well,
is,
this kind of assumes, right, that like after
mm.
the reward is seen, things are gonna be fine.
Yeah,
Which
we'll see. Well, I mean, we'll see more plots later when I talk more about experiments. There we'll actually measure the performance of the policy.
yeah, yeah. This is what I mean. That like these figures are not really telling us that it.
Yeah.
Yeah. Uh-huh. Interesting.
All right, cool. Yeah, so then that much said, let me jump into the algorithm. So our algorithm is called BRIE. It's a shortened name for a very long name. So the full name is called Block Structured Representation Learning with interleaved exploring exploit to emphasize that it doesn't do reward-free exploration, right? It can actually do exploitation as well. So the algorithm is structurally quite simple, right? So given the current iterate of a policy, we do some data sampling. Now the data sampling scheme is a little bit involved, um, but empirically you don't need to do any of these. So what we do actually is we use pi to run to some time step h, and then we do another time step or do another time step of transition using uniformly random action. I did all these are just used for theory, and then we collect a similar data set where we do two-step uniform transition. Now, given that, we'll run some representation learning subroutine, which I will explain more on the next slides. And then we just do this typical linear bandit style bonus, but notice that the bonus is actually using the learned feature rather than the true feature, right? Because the true feature is unknown. And then you run least square value iteration with the learned fee, the data, and the linear bonus, right? So imagine if you do know 5-star, then you don't need step 2. Then everything else is basically what you do for linear MDPs, right? So this is sort of the simplest design you could imagine doing with an unknown phi star. So what are we doing that representation learning subroutine? The idea is quite simple. So we want to find a phi that minimizes this objective. So what it does is I want to find a phi such that for any function f, I want phi to be able to linearly predict the Bellman backup of that function f. Right. So the mean W just means I want to find the best linear predictor based on phi that can kind of fit that Bellman backup of f. And yeah, so this is essentially a linear regression problem on the innermost minimization. And the key iteration is we know from the structure of linear MDPs or lower MDPs, the true feature phi star satisfy the following property, which is it can linearly predict any functions Bellman-Beck. Right? So because phi star can do it, we want our learned phi to also be able to do it. And it turns out that property is enough to guarantee, small regret in the end. Right. So phi star satisfy this property. Now, this is the ideal objective we want to maximize or we want to minimize, but we can't actually do that directly for a couple of reasons, right? The first reason being, inside this term, this expectation over p star is actually we can't evaluate it, right? Because we don't know p star, and you also cannot replace it with naively with the empirical version, because that will give you a unbiased estimator that biased towards f with smaller variance. So what we'll have to do is we'll have to manually correct the bias by adding this term which estimates the variance of f. Okay, so this is the objective now that we're trying to solve. And we don't want to stop there. Why? Because this is like a mean max mean problem, right? There's no way empirically you can solve a mean max mean problem in general. So what we have to do is to design an iterative procedure to solve it. So we show that the following procedure actually converges and give you a decently good phi hat. So what you do is do the following two steps iteratively. You find some phi star, you find some phi t. Initially it can be arbitrary. And then I find the worst case discriminator f that maximize this divergence. And then I find a phi that can linearly fit all discriminators discovered so far. Right? I repeat this procedure enough times. Hopefully, my learned phi in the end will be able to perform well on all discriminators. And it turns out that is true. So now let me introduce the main theorem. So here's the main sample complexity bound for Brie. We're setting a block MDP with, if we assume the trajectory reward is normalized in 0 and 1, then with high probability, Brie can find an epsilon optimum policy with this many epsilon. So we have polynomial dependencies on HD and A, log dependency on the size of the function class, and then we have an epsilon fourth power at the bottom, which seems suboptimal. The two lemma that is used to construct this main theorem is this. So first lemma shows that indeed the learned phi hat from the previous discussed representation learning procedure can give us a phi such that for the maximum f, my discrepancy is bounded by a roughly d squared times square root 1 over n term. Okay, so this thing decreases to 0 as n grows. And this is a side note. So the representation learning oracle is also using Morphle, and we made some improvement on the sample complexity analysis, but the procedure is roughly the same. And given that you learn a phi that satisfies this bound, our second result is actually a type of misspecified linear MDP regret bound, where it says that if you have a phi that satisfies lemma 1, with the distribution rho being your mixed distribution of the policy learned so far, then the final policy you outputted has this regret bound. So here you can see that the second term is a lower order term because it's a 1 over n term. and the first term scale is some polynomial term times square root zeta. Now, because well, that is the wrong thing, right? So because zeta is square root 1 over n, and you take another square root here, that gives us the epsilon to the fourth power here. Now we can actually put together the exact same proof structure for the rep-UCB algorithm. So the lemma 2 will be exactly the same, whereas the only difference is the rep-UCB's representation learning oracle is more efficient in terms of their n dependency. So this is a 1 over n dependency rather than 1 over square root n. Right? That directly contribute to this epsilon square error in the end instead of epsilon to the fourth power. However, notice that the rep-UCB representation learning also depend on the emission distribution function class, which can be complicated, right? Because imagine your raw observations are images, then the emission probability basically encode the probability distributions over all images, which could be very complicated. Whereas the encoder only encode a one-hot representation over the finite latent states, right? So it's a much smaller function class compared to the emission. And so this is something we just worked out recently. So there's actually a very simple reward-free version of both rep-UCB and BRI, which subsumes the previous Flambe and the Malfoy model. So what it does is that in the exploration phase, we'll just run BRI with 0 reward, as expected. And when running BRI for each episode, I, the else vi step will return some estimate of that total reward, right? So this v hat function. And then what we do is we're gonna take the episode where the function the else vi returns the smallest v hat, and then use that episode as a snapshot for the planning phase, right? So for the planning phase, we'll just use the phi hat learned in that episode, the data collected in that episode, and the bonus in that episode. And this turned out to find the exact same regret as in the reward-driven case. I will not go into the details of the proof. It's actually a very smart proof coming out, like Masa come up with it, and we don't have it in the archive version right now, but we'll put it on there soon. All right, so now let me sketch out the proof of the main result. So here we're mainly using two observations. Right? The first observation is that least square value iteration, you can actually define it as if it's a model-based planner. Right? So in particular, if I define my empirical model as follows, so you have phi hat, and this sigma hat times this is basically the linear regression solution. So these two in comparison is kind of a non-parametric model that you estimated, and then we can actually show that pi hat, which is outputted from LSVI subroutine, is precisely what you would get if you do model-based planning using p hat and reward plus bonus. But this is not always true, right? Notice that here p hat is actually not a valid transition, right? In the sense that if you sum over p hat, if you take the sum of p hat over s prime, it is not equal to 1. However, we show that as far as p hat is positive, everything will just work out. You can still apply a performance difference lemma, simulation lemma, and everything like that. It will still work. But this nice property only holding block MDPs. in a linear or in a low rank MDPs, this p hat can be arbitrarily bad. Some entries can be negative and arbitrarily large. Right? So that's the main place where our analysis, why it fails for low rank MDP, but only works for block MDP. Now, in the case of block MDPs, what this means is that we could just analyze the whole algorithm as if it's a model-based algorithm, and that's precisely what UCB, rep UCB analysis give us, right? So the rest of analysis basically apply the same proof rep UCB did. Now, for those of you who wasn't here for Masa's talk, I'll briefly go over the main idea. So the second observation is this very important trick that is used in many low rank or in general bilinear function class type of analysis. So the observation is that for any function f, the expectation of f under some occupancy distribution of an arbitrary policy, it can be linearly decomposed by taking one step back in the transition, right? So you're instead of p d pi h, you have d pi h minus 1, and then that next step transition is decoupled. You split it up by phi star and mu star times the expectation of f. And then you can do a one more step of Cauchy-Schwarz. The first term will be bounded by this, and this is precisely the elliptical potential kind of term, right? You have your true feature phi star and your true covariance sigma, and then the second term can be bounded separately. So this is how we can sort of extract a phi star freely from the expectation of any function, right? Even though we never know phi star in the algorithm. Given that observation, the proof mainly consists of two steps. So the first step is to prove optimism. Now, instead of a point-wise optimism, here we are able to show a trajectory-wise optimism. In particular, we can show that for any policy, the value you get out of the empirical model and the reward plus bonus is almost always bigger than the value you would get out of the true MDP. So here, the first step, I just use performance difference lemma, and then I'm going to show that the expectation of the bonus is larger than the expectation of the discrepancy. Now, given optimism, I can decompose the regret as follows. Again, I use here I use performance difference lemma. So the regret is upper bounded by here I replace px r p star r with the empirical transition and bonuses. So this is the optimism, and then I decompose this difference to be the expectation of the bonus, and then the discrepancy. And then here is when I apply the one step back trick. So I decompose this term into the product of two terms. The first term is precisely the elliptical potential term, so it's bounded by square root d times n. And the second term is bounded by a constant. So that is essentially how the proof goes. All right. Any questions on the proof? This is lower bound.
I guess this last step wasn't fully clear to me. I mean, I can see how this elliptical potential thing works out, but the other term.
Yeah. So yeah, let me go over the other term. So, so the first term is the expectation of the bonus under the distribution. Like this is the data generated distribution, right? This is the bonus you constructed under the same distribution. So this expectation is naturally bounded by square root d. And the second term, so this is your discrepancy, right? So recall the representation subroutine is precisely bounding the the expectation of the discrepancy under the training distribution rule, right? So this Cassie term is precisely bounded by square root zeta. All right, so that is from the representation learning guarantee, and this is naturally bounded.
Okay. So just again, just to see if I understand correctly. So you take an expectation of this B hat under the data distribution that you get using the role in policy. So this is like the actual data distribution that you see.
Yeah.
But then these terms are not bounded individually, right? It's only their sum that is bounded in total, right?
Yeah, it's not bounded in. You mean the B hat is not bounded individually?
Right.
Yeah, they're not bounded individually. They're only bounded under the same distribution that you constructed with. Yeah.
Right, but still, I guess you need to sum up over n as well eventually. No? Maybe I'm just not getting what n is.
No, because B hat is the unnormalized version, right? So B hat gets smaller and smaller when n gets larger and larger.
Oh, okay.
Yeah, because it's the bonus, right? So,
I see. Okay. I get it. Good. Thank you. All right, I think we can go on.
should I continue? Okay.
Question. What was capital sigma?
Capital sigma is that covariance defined all the way back here. Like this is sigma. So it's unnormalized covariance plus some regularizer.
It's for the empirical features. It's not for the true features.
It's for the empirical features, yes.
So
I mean, okay, so in this decomposition, actually, we're using it for the true feature, I believe. Because in the Cauchy-Schwarz step,
yeah, you introduce
you can use any,
that's why I'm
matrix
asking, like, which one are you using there?
I am using the true feature.
Okay. Here. All right. Okay.
Yeah.
Okay. That's what I.
That's why the first term can be bounded. Otherwise, you have trouble.
Right.
Yeah.
Okay.
Yeah.
And so in the second as well, you have that one.
Yeah. In the second, because sigma comes into this rho term basically, right? Because rho is that true distribution, which is constructed using the true feature.
Right.
Yeah.
Okay. Thanks.
Yeah. Cool. All right, so now let me talk about the implementation. So one really good thing about BRI is that it's really easy to implement, right? So there are two things we need the function approximation on. First thing is this phi class, right? Now in this particular block MTP environment, because we know the phi is a one-hot encoding, right? Because the latent state is tabular. Here we just use a softmax encoding on the state. And then it just do a Cartesian product with the one-hot encoding on the action. Now here, this is just like a one linear neural network, or I mean, just a linear function. And this is because our encoder in the actual environment is a linear function, but in general, you can plug in any neural network in here. And then it's for the function approximation of the discriminator. So this is what I didn't touch on in detail previously. So in the proof, there is a the curly f discriminator function class. This class takes a particular form, but that form is only really useful in the proof just for the covering argument purposes. But here, I mean, the intuition is that we really want our phi to be able to linear predict a diverse set of functions, right? So then actually for the discriminator, as long as we use a expressive enough function approximation, we'll be fine. So in this particular implementation, we're using a two-layer neural network to represent the discriminator. then that's pretty much it. So here again is our sparse reward block MDP, and notice that it takes both Bray and Homer to roughly 3.5 billion episodes to solve this, right? This is a sparse reward example. Now, what happens if I now inject some dense reward into the environment, right? So if I add some positive reward to these good state transitions, then intuitively a greedy algorithm should be able to perform pretty well, right? Because the reward, the immediate reward actually indicate what you should do in the long run. In this case, you can see that Bray's sample complexity reduced drastically. So this is on the y-axis. Now it's actually the performance of the learned policy. But Bray actually only takes 10K episode to learn the optimum policy here. And we didn't plot Homer here, but because Homer is a reward-free algorithm, it would take the same number of episodes as if the reward is sparse. Right? And in comparison, we have a greedy algorithm PPO, like a local expression algorithm. It takes roughly 2 million steps to solve this problem. So Bray actually takes much less, like 300 times fewer episodes compared to Homer. And another thing that you might be curious about is how good is your learned representation after all? Even if you can solve the problem, is the learned representation reasonable? It turned out that it is, right? So here I'm visualizing the learned representation for a length 25 combination log. You can see most of these is probably too small, but you can see for most states, the encoding for that state is actually concentrated on one entry rather than spreading out between several. That means on most states, it is able to encode that state into a unique latent state, which are distinct actually for all the true states. They're different, right? So they actually recovers the latent state almost perfectly.
Can I ask a question about this?
Yeah.
So this is with this 10 age thing, single layer or 2-layer, or what is the state decoder function class?
The state decoder is a single layer, basically linear function,
The
and
10
a
age
softmax
that
on top
was,
of that.
yeah, okay, the 10 age that
Yeah.
was shown on 2 slides ago or something.
That's right.
So that's the if you apply the theory to that, it seems that that would say that you need, the sample complexity or whatever metric you're using is going to scale with the number of observations because it's at each class. It could,
No,
in theory,
no, actually,
it's not.
it's not a 2-layer 10 network. So that 2-layer 10 network is approximating the discriminators. This phi is only a single layer. It's basically a logistic function.
So I guess I'm wondering about, okay, so S has this one hot representation. AH is an arbitrary matrix that is trying to compress the one hot representation to another one hot representation, or
so S is not one hot, right? S is that rich observation. So it's actually a dense vector, but we're trying to decode it into a one hot representation on the latent state.
I see. So what was that dense representation? Can you show me again?
Yeah. So the actual representation. So we take I don't have it here, but so the latent state is a one hot encoding of the state, right? So if you have 100 state, it will be a one hot encoding of length 100. And then what we do is we add random noise, add Gaussian noise to each entry of this vector, and then do a random linear transformation on top of this perturbed vector. So that would be the state that you get eventually.
Okay.
Like that's also why like a linear, because we know a linear transformation on top of, you know,
it's gonna be
softmax is enough, right? But you know, in practice, if you have more sophisticated environment, you might use richer classes here.
yeah. So what's the covering number for this? If you have S observations Z latent states, it's linear in S.
The latent state is like a generalized linear function of S.
Right.
Yeah, so the covering number would be like OD. It's a linear in D. D being the raw observation dimension size, in this case 100.
I see. Let's see. Okay, yeah, thanks. That makes sense. If you, yeah, like if you wanted to have a sparse representation for whatever, then okay. Then the
Yeah.
D would be the number of observations, but you can have this dense thing and then, okay. Yeah, thanks.
Yeah, no problem.
Makes sense.
Yeah. So actually talking about that sparse representation, actually we show that algorithm, you know, doesn't really need that. Like what, right? So in this experiment, we'll kind of explore, you know, what happens if I don't have a block MDP. Rather, I have a general low rank MDP. In particular, in this case, we assume there's a the feature is, instead of being one hot, is a simplex. So each observation, it maps to a distribution over latent states, right? So then, you know, going back to the question at the beginning of the talk, in this case, the latent states are no longer decodable. Right, so in this case now, Homer doesn't work because Homer is specifically designed for block MDPs. So we compare with some other baselines. So the purple line is the LSVI used to be algorithms with the ground truth feature, right? So you would expect it to work and the sample complexity to be pretty small. And the blue curve is ours. So at the start, it takes some time to learn that true representation, but then it quickly catch up in terms of a policy performance. However, you know, as previously shown, the PPO plus R&D kind of empirical baseline still fails. Right. So that almost conclude my talk. So just to summarize, in this
So
talk,
just quickly, actually, I was asking whether in this experiment, Breeze not guaranteed to work, and yet it works.
in this experiment, yeah, exactly, yeah. So the theory actually doesn't say that it could work, but it actually works. Like this is a kind of backstory because we've always like, even from the beginning, we were trying to design Breeze to work for low rank MDPs. It's just that the theory part is one step that it doesn't work through. So that's why we can only get it to work for block MDPs. But there's no reason to believe that the algorithm itself actually is restricted to block MDPs. Because throughout we're using the linear, you know, the low rank MDP learning procedures, basically. This experiment actually have good reachability. You can reach all the states with probability 1, almost. I mean, not 1, but constant probability. Yeah.
Okay, then do you know why PPO and R&D fails?
So, I mean, my personal suspicion is that you know, because for this long chain of combination lock, you really have to do a precise sequence of actions to reach the action. I mean, to reach the final reward. But PPRND is kind of a randomized algorithm, right? Because it's a policy gradient based algorithm, right? So then because of that randomness, it just makes it much harder to hit the target. That would be my guess. If you were to use some, I don't know, value-based method, maybe it will work. But the R&D part also has randomness, so it's hard to it's hard to say.
Thanks.
All right. Yeah, no problem. Yeah. So yeah, just to summarize, in this talk, I present a simple and efficient representation learning algorithm for Block MDPs. It is adaptable to reward-free setting, and the implementation is also easy, and it has competitive empirical results. Now, so you might ask, what's next? When we do representation, we don't just think about the performance on a single task, because otherwise you could use more end-to-end approaches where you just directly learn the value function on top of the raw inputs, right? But one advantage of doing representation learning is that it's able to be shared across tasks or to new tasks. So we actually have an upcoming paper on this where we show that by doing representation we're able to do multitask and transfer learning in lowering MDPs, where we allow both like online learning in both source and target tasks. And this is much stronger than prior works on transfer learning in RL. So hopefully the paper is out maybe 2 weeks from now. So yeah. And finally, some references for the RepUCB and Bree paper and the code you now put together. All right, thank you very much. And I'm happy to take more questions.
Yeah,
Cool.
very
Thank
nice.
you.
Thank you. All right. So while people are thinking about questions, maybe I can have like a quick technical question that you said at some point. Maybe I just didn't pay enough attention about that point that you were making about the model that LSI UCB uses. You said that it's not a valid transition model, but it's
yeah, let's look at that part.
But it's pointwise positive, or what was the term that you used?
It's pointwise positive. Yeah.
Okay, and what does that exactly mean?
Oh yeah, so point positive means like if you evaluate this transition on any SAS prime, it will be a positive number.
Is that right? And does this have to do with the block MDP structure?
Yeah, this has to do with block MDP structure. Like, so if you actually write this thing out for block MDP, it's basically the like tabular MDP type of transition where you would count like say if SA and as tilde correspond to the same latent state under phi hat, they will count as the same state, right? So then you can transform, like given phi hat, you can translate the whole data set into a tabular data set on a Z, right? So then you basically construct a transition model using that latent states data set. So this will be a tabular transition model, but it's not a valid transition because there's a regularizer inside sigma, right? So when you translate it into the tabular empirical transition, basically you have a +1 or plus lambda in the denominator when you calculate the transition. So actually here there will be their sum will be strictly smaller than 1. It will be like n over n minus n plus lambda, something like that.
I see. So if these phi hats are one hot vectors, right? Then
yes,
and this sigma is a diagonal matrix, right?
Yes. Yep.
I see.
So you actually recover the whole linear, tabular, tabular thing.
Okay.
Yeah,
Okay. I see. I get it. But then in your implementation, when you're not actually working with one hot vectors, But with these
Right,
soft text things.
right, because empirically it's hard to work with a one-hot encoding and make it differentiable, right? Like if you want an exact one-hot encoding, it's not that easy.
But I guess you converge fairly close to an exact one-hot coding.
Yep, that's right. Yeah. So that's one good
but
sign.
you did have some states for which this was not one-hot actually. Right?
Yeah, there are
was
some failure cases. I think those are the starting state. Right, it's just that first state that it doesn't converge, and this I think is because I mean maybe Yuda can comment on this. I think it's because two of the states are actually not distinguishable from their transition in this starting state, and that's why the algorithm can arbitrarily mix them up because from the algorithm's perspective they just look like the same state, right? So the one-hot encoding doesn't have to pick one versus the other. It can be any mixture between the two.
Actually, for the first time step, you only have state 0 and state 1, so it's fine.
You only have state 0 and state 1.
Yeah, because you cannot start in the best state and stay there forever. Yeah.
Yeah, so you actually never see state 2 in step 0. And for these two, it's kind of like this is 0.98 and this is at 0.8 something. Yeah, that makes sense.
So the implementation, can I jump in?
Yeah.
Question. So this representation learning part,
Mm-hmm.
so it was solving iteratively this min-max mean problem, right? What's that?
Yep. Here.
Right. Yeah, it's generating these phi's in an iterative fashion. So here you're running a gradient algorithm until it converges based on all the data that you have, or what is happening here? Step 2.
Oh, it's
and also
running.
step 1. I guess like I'm also curious about like how do you implement step 1? So what are the discriminators that are being used?
Yeah, so in the result I show that for the discriminator we're using that two-layer neural network. So basically for each step I train a fresh network F to do this maximization problem. Right, so this F is code star from random network, and then I train it to converge.
Can I ask a question for the theory? This discriminator class, it needs to be chosen in some specific way, and in what way?
Yes. Yeah. So it's similar.
Yeah.
I didn't put it here because it's quite complicated, but it's similar to like the covering argument in linear MDPs. You want to choose the discriminator to cover all the linear functions on all possible features, and then on the difference of all possible features, basically. So it's a function class of covering number on the order of d square.
Oh, I see what you mean.
Yeah, but I mean empirically, there's no reason to use a particular design like that.
It's basically you're saying that make that powerful. Like the theory is kind of also saying that that should be powerful enough.
Yeah, exactly. Yeah.
And have you looked into that? If the theory could accommodate a specific choice of this discriminator functions?
We needed to include certain functions, right? So as long as it's richer and include all the functions we needed to include, then it's okay.
So if there is some misspecification with this, like how robust the results would be?
It wouldn't be robust, I don't think. Like if it doesn't cover some term, that term can be
maybe approximately something. Yeah. Doesn't matter.
If there's a distributional notion of how much it covers, then maybe that is okay. But if you only have pointwise, say cover or not cover, then I think it wouldn't work.
Okay, so you have to kind of do it pointwise. Okay, so that was the first question, and the second question was like, how do you implement step 2?
Step 2 is, I mean, given all discriminators, this is just a linear regression problem, right? I mean, it's a linear regression on top of phi. Right? So phi is a function. Well, itself, you can think of it as a neural network that we'll keep minimizing. I think we just run a fixed number of iterations every time step. Yeah.
So it's a regression problem, but it's a nonlinear regression problem.
It's a nonlinear regression problem, exactly. Yeah.
Yeah, but an age.
Like actually, so I just want to briefly say this. So actually, for the first step, like currently we're thinking we don't even need to do this maximization, right? If I just have a set of random networks that we believe are,
good set of discriminators,
diverse enough, yeah, then you can just do step 2 and get it done with, right? So
right. But in your implementation, you were basically following this step, and
yeah. In the implementation I showed, that was when we were writing the paper.
Yeah,
it is following the procedure more
so
closely.
so here the cost is going to increase with t growing, like whatever t is in this slide. So I don't know how fast you made that cost grow in the experiment. Like, how do you? Is there a tuning parameter there?
What do you mean by cost? Which cost?
Like computational cost.
Oh yeah.
You're storing more and more of the discriminators, and then you are
that is true.
a criterion that it was. So it's like a quadratic cost. If you literally implement this, unless you try to do something more clever.
I think we're just saving all those discriminators as far as I can recall.
So then the compute cost can be pretty heavy.
The computation cost, you mean in terms of evaluating this objective? The more discriminator you have,
or even like you need to optimize it, right? Like the whole algorithm.
Yeah.
This is a subroutine for the whole algorithm. Like
that's why we thought, like, if we can just take away step 1, it will be much faster, right? Because step 1 requires you to optimize the network every iteration from scratch. If that step can be discarded, then the second step is actually relatively simple.
Have you tried that?
Have we tried that?
Yeah.
I don't know.
I mean, it would be faster. It would be interesting to see whether
maybe we're trying it in the current iterate. Do you want to comment on that?
No, we haven't tried that yet.
Okay. Yeah, because like we were thinking, if we want to extend to like a target game kind of environment, we definitely have to do that kind of implication.
Yeah, but like in this case, the discriminator class are actually pretty like benign comparing to like those deep learning neural networks. So we actually optimize do all of the optimizations on CPUs. We don't even need a GPU to do all the heavy lifting for us. So computational wise, it's actually pretty okay because of the size of our function classes.
Yeah. Actually, it was also pointing out that the bonus could also become expensive to calculate over time.
The bonus, yeah. I think this is come from for all linear MDPs, right?
Yeah.
This bonus, yeah.
And so he was wondering whether you have any ideas about how to speed it up by maybe make some reasonable compromise there.
Like, well, I guess not necessarily calculating the bonuses, but optimizing over the action. Selecting the actions.
Yeah. Because like in linear MDP, you can potentially, iteratively calculate this sigma inverse term. But here the problem is this phi hat is different every time. So right? So you actually it makes it easier. It makes it harder to do any kind of speed up.
This is even
so,
worse.
yeah,
I mean, maybe you can
this
use
is,
that phi hat is slowly changing or something. But becomes dirty.
yeah. That's probably doable. But in practice, I mean, it's hard to say like how, unless you constrain how much your phi hat can change every iterate.
Maybe
Otherwise,
it's already constrained because you're learning in a incremental fashion.
like in practice, I think the easiest thing to do is probably do a low duration cost version. Like you just don't update it very frequently, right? So
Yeah,
well,
right.
yeah. Yeah, there are a lot more things to try empirically.
Yeah. Cool. Right. Thanks.
Oh yeah, my pleasure.
Oh, well, of course, the bonds. You have 8 to the power of 9.
Oh, let's look at that. Yeah. 8 to the power of
14. 14.
yeah,
H to the
like,
power of 9. Z to the power of 8.
yeah.
And I guess the dependence on epsilon is probably real because you have this double loop and kind of
So that's also a point. So this is, I mean, this is also already studied in the Malfoy paper. So I do not claim this to be my contribution, but like if I assume I can solve this min max min problem perfectly, right? Then actually the sample complexity is 1 over epsilon squared. The actual
But what do you mean by perfectly?
I mean, like literally, if you can, sorry, not this objective, this objective, right? So if you can solve this perfectly, so these are all the empirical data set, right? So this is a empirical problem.
So this is all empirical.
Yeah, this is all empirical, but it's a min max min problem. If you assume you can solve it perfectly, then the sample complexity is 1 over epsilon squared.
So just let me understand this. So you have the iterative algorithm, and the guarantee for the iterative algorithm is not that if you keep running this algorithm, it's going to solve this problem perfectly, or is it?
So the guarantee is the following. So it's saying if I run this algorithm for a fixed number of times, for a fixed number of iterations, it's going to give me a phi hat that approximately solve this objective.
But okay, so we fix the data, then we can run this iterative algorithm, and we can solve this problem at any accuracy we want.
Not at any accuracy, at some accuracy depending on the number of data.
How come? So that's not an optimization result, then like somehow it uses a structure of the problem. Oh, so, okay, I guess I don't understand.
Oh no. So we're actually saying we can solve the true optimization, the underlying optimization problem, right? So if you replace this D with the underlying distribution.
Right. But I'm just asking the question, okay, but like if you have this result, then that kind of suggests that maybe you can just study the optimization problem on its own.
Right. Yeah, we totally believe that the true sample complexity here should be 1 over epsilon squared, just because
So then basically you're saying that this is just like a slightly lazy algorithm that if you would spend more on computation or you don't limit a computation, then the epsilon dependence should be epsilon squared. And the computational cost in terms of everything should still be polynomial.
That's right. So here we have a polynomial dependency on everything.
Yeah.
But if you actually if you run this, because this iteration is at most the number of discriminator number of iterates, right?
Yeah.
So if you run it for that many iterate, then you basically solve this precisely. Then you get the whatever you want. But here we just want the sample complexity to not scale linearly with any of the function classes.
Mm-hmm.
That's where the slack comes from.
Okay. All right. So epsilon issue is kind of fixed. So that remains the issue of dependence on horizon and number of actions and all that, a number of latent states.
Right. I mean, because from this decomposition, we really know like all the slack comes from lemma 1, right? If we're satisfied with the rapid UCB result relatively, then lemma 2, there's nothing to improve in lemma 2, really.
Mhm.
Everything comes from that. But I mean, you expect to pay something, pay some defactor here because you're not using a mu function class, right? You're using discriminator, so there should be some defactors you pay.
Mm-hmm. Mm-hmm. Mm-hmm.
Yeah, like I think right now what we want to solve the most is how to generalize it to lower rank MDP, like how the current proof. We've tried many things, but all of them
Mm-hmm.
failed. Yeah.
Mm-hmm. And the failure is in this first step,
In the very first step, yes.
fact one. Okay.
And also like inside lemma 2, there's some defactor in here, which is actually the norm of that p hat basically, right? Like so, like for block MDP, that norm is bounded, but for linear MDP, that norm can be arbitrarily large.
I see. I see. Okay. Well, interesting. Maybe the proof needs to be changed.
Yeah. Because right now, the only way we know how to prove these are from a model-based approach. Right? It's completely model-based proof, even though the algorithm is model-free.
It's like,
Yeah.
what is model-based? What is model-free? I don't
If
If you put the data, then you have the model of the world.
Oh yeah. But like model-based, I guess, is where you explicitly reason about the the value under these empirical models versus true models.
Yeah, but you can argue as well that if you keep all the data to approximate empirical means across over different functions, then you really have a non-parametric model of the transition kernel.
Yeah, that's that's exactly what we're using.
In a way, that's what's happening.
Yeah. I mean, even in LSVI analysis, I think you can also put in a model-based analysis, but it doesn't scale with anything about the norm of the p hat. So their p hat doesn't cause a problem, but in our case, it does. Yeah. So maybe yeah, I don't know.
So in this sense, like, is there any real model-free analysis that doesn't use any of these ideas? There is.
I mean, the only model-free analysis isn't that just the Shijin's Q-learning paper, UCBH for tabular MDPs.
Right.
Because anything that saves all historical data, you can think of it as model-based, right? In some sense.
Right. Yeah.
Yeah. So, and that only works for tabular MDP. So. I mean, even empirically, DQ1 saves all the data, right? It has to use historical data. So I don't know.
Sure.
If
Well, maybe it's not a problem. Yeah. It's just.
yeah. I just wonder if model-free learning is actually a thing, or it's something we hope to be true, but it's not. I don't know.
Right. Yeah. I guess this relates to how fast your algorithm is and how much memory it uses at the end. But
yeah, definitely.
Okay. Yeah. Thank you.
My pleasure.
All right. Anyone else? Some questions?
Yeah, the chat is very quiet.
Well,
Everybody
it was not
all their
quiet for
answers.
now, but now. Well, I'm pretty happy with everything. So, there are no further questions.
Yes, wonderful work.
Yeah,
Very nice one. Very
Alright.
well presented too.
looking forward to
Thank you very much.
next steps.
Yeah, we're quite excited about that coming paper. Yeah.
Cool. All right, thank you.
Thank you very much.
Yeah.